Hello, everybody. I made these slides for students who feel like they're working really hard, but they're not getting an A, and they want to know kind of how can I level up in pre-calc honors. So here's the plan. I want to talk about how A-level thinking is different from B-level thinking, and things that you can do in class and things you can do at home to shift how you approach the problem sets and how you approach notes and how you approach asking questions to kind of shift from this B level up to the A level. So let's talk about how is it different. So here's an example of not A-level thinking. So in math class, it's often the case that you just need to master some particular facts and techniques, and that the problems are going to be similar to ones you practiced on. And so in that case, the way to succeed is asking yourself, what do I do for this kind of problem? And remembering the steps, and then being able to do the steps correctly. So doing procedures like that, math teachers call this procedural thinking. So being able to do procedures like this isn't particularly helpful because we can have computers do these steps faster and better than you can. So definitely it's important, but especially in an honors class, that shouldn't be enough to get an A. You can do these things just if you have a good memory and good attention to detail, but you can do them without any real mathematical understanding or insight. So that's why I'm trying to help you develop your understanding and insight, and that's what the rest of this talk is going to be about. It's how can you start to do that. So instead of A-level thinking, now I'm going to call it mathematical thinking, because that's really what we're talking about here. But that's the kind of thinking that in the honors class is worthy of an A. So before people have developed mathematical thinking, here are some kind of situations that they often find themselves in. They might get stuck on a problem, and the only thing they can do is ask for help. Like they might ask a classmate or they might ask the teacher. They have to ask, is this right a lot, or does this make sense? Because they don't have any way of deciding for themselves if it makes sense or if it's right. They need some authority to tell them. If you find yourself doing this, that's a sign that you haven't developed mathematical thinking yet. Because if you think about it, you'd only have to do these things if your understanding is based on memorizing rules. Because if you've just memorized some rules and you're stuck, there's no possible way you could invent the rules for yourself. Or if you are not sure if you did the rules right, you need someone who knows the rules to tell you, yes, you did them right. The difference between that and mathematical thinking is you can think for yourself when you've developed mathematical thinking. You can make rules on your own that make sense for a problem. And you can check to see if those rules make sense because you understand why the rules work in the first place. So if you get stuck on a problem, there's lots of things you can try to get yourself unstuck. You know your rules make sense because you can check them. So developing mathematical thinking helps make you more independent. So now I'm going to go through a whole bunch of specific examples of what this mathematical thinking looks like from problems that have happened earlier in this year, before we talk about how can you start to adjust your thinking in class and at home. So there's roughly 3 categories of example. Actually, I'm going to add a fourth. So one is why do certain ideas work that we talk about in class? And can you apply not the rules to new situations, but can you recognize the same reasons as applying to new situations? So here's an example that we might do in Algebra 2 trig. So in Algebra 2 trig, you learn how to solve equations by factoring. So you factor, and you learn that if the equation looks like this, it means that either x minus 2 is 0 or x plus 3 is 0, so the solutions are 2 and 3. If you just memorize that as a rule, you wouldn't be able to adapt it to new situations. So if you look at problems 1 and 2, can you use that same rule in question 1? Can you use the same rule in question 2? Not really clear. I'm probably not going to solve all of these in the talk because that would make it very long. But the underlying thinking here, called the zero product property, is the idea that we are like x minus 2 is just a number and x plus 3 is just a number. And so if you're multiplying 2 numbers and the result is 0, you know that either the first number has to be 0 or the second number has to be 0. That's the only way you could have 2 things being multiplied and get 0. And so that's what gives us these 2 equations. Either x minus 2 is 0 or x plus 3 is 0. And then you can solve the equations separately to say what value of x would have made that happen. So down here, you can see the same reasoning doesn't apply. I can't say either x minus 2 is 1 or x plus 3 is 1, because that's just not true. I could come up with a value of x where the product of both of them equals 1, but neither one of them itself was equal to 1. This looks very different on the surface. I don't have this nice x minus a thing structure. Here I've got a rational expression, and here's just an x, and here's a 2 to the x. But you can see that the underlying structure is the same. I have 3 things being multiplied, and so I know that if this whole thing is going to be 0, either x is 0, or this part is 0, or that part is 0. And then you can think about each of those pieces separately. So learning to spot the underlying structure in a problem instead of looking for surface level similarity. That's one big thing that you can start trying to practice to develop A-level thinking. Let's do another one. So we've seen this example since the very beginning of the year. For the function 1 over x, as x approaches infinity, f of x approaches 0. And recently I asked people to come up with 3 different kinds of function other than 1 over x where this same thing is true, where as x approaches infinity, f of x approaches 0. And it was very striking to me looking at people in class. Some people were immediately able to come up with some, and other people sort of were like looking around like, how on earth would anybody possibly come up with this? So hopefully you can recognize this as an example of figuring out why is something true, and how could you apply that same reason in a different situation. So the reason this is true is because as x gets larger, the denominator gets larger. And as the denominator is getting larger, like a constant divided by a larger and larger thing, becomes smaller and smaller towards 0. So other functions would be 1 over x squared, 1 over x cubed, 1 over 2 to the x, sort of any function where the numerator is constant and the denominator is increasing. Okay, let's do a last example in this category. So we did this analysis for end behavior of rational functions where we looked at dominating terms to decide where horizontal asymptote was going to be. So all the examples down here, they're not rational functions anymore because I've put a sign in there. In order to be a rational function, it needs to be a polynomial divided by a polynomial. But you can still think about the analysis that we gave in terms of dominating terms and decide, does that same analysis seem to work in these various cases? Why or why not? So again, to bring out the contrast, procedural thinking, a student might think to themselves, oh, what are the steps I need to know? And how do I do those steps? Like, what do I need to know in order to find the answer? Students with mathematical thinking are thinking, why do those techniques make sense? Would they ever not make sense? Like, what would be a situation where they wouldn't work? Why? Why do they work? So they're trying to understand the limits of the rules, and they're trying to understand the underlying reasoning. And this is really, again, it's very evident in the questions that people ask. Like, oftentimes the students in class who have mathematical thinking, when I ask if there are questions, they ask things like, would this work if? And then they come up with a new scenario. And that shows that they're on their own trying to think about why the underlying reasons make sense. Or a student the other day asked, would this same analysis tell us? And then she suggested some other thing that's not the end behavior, or some other aspect of the end behavior. So you can see that the students who are already getting A's, when they listen to lecture in class, they're not focused on what are the steps and what do I do to get an answer. They're focused on what's the theory being explained and why does it make sense. Let's do another example. So in Unit 1, we were talking about the domain of a function. So we learned that because the denominator can't be 0, here the domain is x not equal to 0 or negative 2 or 3. So here was an extension level question that I asked a couple years ago. Let's say we have a function f of x that's pictured here. What do we know about the domain of 1 divided by f of x, or 1 divided by square root of f of x? That might seem very obscure, because I don't even have an equation for f of x. So the problem doesn't look anything like this problem. Here you can do it by pattern matching, or you could do it by looking at surface level similarity. You'd say, oh, here I see, if the denominator is 0, that'll tell me the answer. Here you have to kind of think about what do you know about calculating domain. You could think, oh wait, if the denominator is undefined, or sorry, if the denominator is 0, then the entire fraction will be undefined. And then you'd ask, how do I know when that might happen? And so over here you can see some zeros of the function. So at -2 and 0 and 3 are all times when f of x is 0. And so you can connect the dots. So you can say, oh, if x is -2 or 0 or 3, that would make the denominator 0, which would make the entire function undefined. So it's really the exact same question. I just made it look different on the surface to try and test, can people think in terms of reasons? Can they ask, how would I know if something were true? Where could I get that information from? Okay, let's do another category of mathematical thinking. So if you get stuck on a problem, do you have strategies to try and make sense of the problem in another way than whatever it was that you were shown directly? So let's imagine this equation. Could an Algebra 1 student solve this equation? Really, it's an inequality. I'm going to call it an equation, though. So you could imagine students saying, well, we don't know how to undo exponents, or I've never seen an equation like that before. And that's the kind of answer that students who are used to learning procedurally would give. So that's students thinking, what do I do to solve the problem? A student who's thinking, what is this problem really talking about? What does it really mean? They might be able to come up with strategies. So if I think about what this inequality is saying, it's saying, what's an x value that would make the equation true, that makes the inequality true? So like, what's an x value I could plug in where this whole thing's going to be less than 0? And if you think about that for even a minute or two, you could start testing some x values, and you might immediately start to come up with an answer. You could say, oh, 2 to the x, no matter what x value I plug in, it's always positive. And then we add 3 to an already positive number, so it's never going to be less than 0. Or you could think in terms of other representations. You could think about a graph. This is an exponential shifted up by 3, and you can just see based on the picture that it's never going to be less than 0. So what I'm trying to emphasize is even Algebra 1 students could answer this question very easily if they developed a mathematical thinking approach to the problems in class. And if you haven't yet, I am not blaming you. I'm not saying that you're bad. I think school encourages students to think procedurally. It's the most efficient way to solve most math problems that school gives you. The problem is it's not a very useful way of thinking in the real world. So that's why I'm trying to encourage you to develop, a more problem-solving approach to thinking. So here's an example from our class. This was one of the A-level questions in semester 1. So consider this vector sum. I've got this big vector and this big vector, and it says find the magnitude. So without a calculator here, we can't make any progress. And a lot of students really wanted to compute things computationally. They wanted to actually find the numbers and add up the numbers. But I designed this problem so that that's not possible without a calculator. You don't know what cosine of 5 degrees is or 95 degrees is. But one thing that I said consistently every single day from the very beginning of the unit was that it's helpful to think of vectors in two different ways. You can think about them computationally, or you could think about them geometrically. And there's a lot of insight into thinking about them geometrically. And so in this problem, I would think, okay, cosine 5 degrees, that's, at an upward angle by a little bit, and then 95 degrees is kind of 5 degrees more than vertical. You'd see that these are at right angles to each other. One is length 3 and one is length 5. I can tell by the scale factors. And if I'm adding them together, I just add them ends to end. So if I want to know what's the magnitude of v, that vector is v, and the magnitude of v would just be the Pythagorean theorem. So the question is immediately solvable if you just ask yourself, is there another way of thinking about this? And to be clear, the other ways of thinking about this are never going to be surprises. It's never going to be something weird that you've never seen before. Here, the other way of thinking about the problem was something that we'd said every day and that a lot of the problems in the classwork required of you. The difference between students who got this question and students who didn't, I think, really is in this fundamental approach to problem solving. Students, sometimes in class when I said think about it geometrically, some students would be like, oh, okay, this is a problem I think geometrically. Oh, okay, this is a problem I think computationally. But they never developed the ability to ask themselves, oh, should I think about it in a new way? How else could I think about it? So here we are so far. We've got two categories of example. Why do ideals work, and can you apply those same reasons in a new situation? And part of that is being able to see the underlying structure of a problem and not just its surface appearance. And the underlying structure is related to the reason why rules work. So if you're wondering how on earth do you see the underlying structure, that's a big part of it. Another category was, if you get stuck, are there other ways of making sense of a problem? And that's why we have multiple representations, thinking about things graphically, geometrically, numerically, with a diagram or with an equation. If one of these, I think students very often gravitate towards numeric and equation, but there's a lot of insight to be gained from graphs and geometry and diagrams. And so I think being able to flexibly switch between ways of thinking is a big item in this area. Related to that is, even within equations, there's different forms. So these are two different forms of a parabola, and they tell you different things. Here, the standard form is really great if you want to know what's the y-intercept. Here, the root form is really great if you want to know what are the roots or the x-intercepts. So if I give you an equation in one form, but you want to know something else, like what are the roots, realize that you might need to transform it to a different form to learn a new thing. Okay, last category before we talk about some practical tips. You might need to explore a situation a little bit by testing some examples and seeing what they show you and deciding what they mean. So here's an example of that kind of problem. Let's pretend I have an unknown vector A whose length is 4 and a different unknown vector B whose length is 5. I want to know what's the magnitude of 2A plus 3B. Well, because I didn't tell you very much about A and B, there's lots and lots of possible answers to this question. And in order to get a feel for the problem, you might want to sketch out a whole bunch of different examples of what are vectors whose length are 4 that are different from each other, and what about vectors who are length 5, and what would it look like if you were going to add them together like this. So I want to know what are two specific vectors where that is going to be as large as possible. So it's impossible in this question to just magically know the answer in your mind. You have to tinker around a little bit and visualize what the possibilities are. But as soon as you start to do that, I don't think it's an intrinsically very hard problem. Here's a different example. So here's a piecewise defined function and a different piecewise defined function, f and g. How can you think about the composition of g of f of x? We never talked about composing functions that are defined piecewise. Here the problem itself seems to be suggesting that the composition is itself a piecewise function. But again, it's not really at all obvious how you just jump straight to the answer. Like, I don't even know, this one has 3 pieces to it, this one has 2 pieces to it. What about the composition? Does the composition have 3 pieces or 2 pieces? I don't know. But you can start to tinker around a little bit. You can start to imagine, what if x was less than 0? Like, what are the different things that might happen? What if f is between 0 and 1? What are the different things that might happen? And so you can imagine with individual numbers performing the composition. And then you can step back and you can say, okay, so what patterns do I see here? And then you can start answering questions like, how many different pieces would there be? What would the different domains be? And then what would the actual functions be? A fourth category, and all of these categories overlap with each other a little bit, is asking yourself, what would it look like if something were true? How would I know if it was true? What could I check for? So here's a function that a student came up with, actually. So 3x plus 1 plus x over x squared plus 1. And this has the general form of something with a slant asymptote. Here we've got 3x plus 1 is the slant asymptote, and that's the remainder term. The question is, does f ever cross its own asymptote? So you have to be able to think about the meaning of the parts. The reason that f has a slant asymptote is because the remainder term approaches 0 as x approaches infinity. And so you think about the remainder term as being the amount that the y value is adjusted either above or below the asymptote for different x values. So if f crosses its own asymptote, how would you know? It must be the case that for some x value, the y value is just exactly equal to the asymptote. And so you could solve for that situation. Or equivalently, you could think, okay, the remainder term has to be 0. And then you could see, oh, if the numerator were 0, then the whole thing would be 0. So again, it's a question that I'd never asked before, but if you understand the meaning, or you have different ways of thinking about the meaning of the pieces involved, you could ask, what would it look like if it were true? And that immediately suggests a direction to go. All right, so let's wrap this section up. So how is A-level thinking different than B-level thinking? So it's these things. Students who kind of are stuck in the B-level are stuck thinking procedurally. They want to know, what are the steps to get the answer? A-level thinking, you want to practice all the time asking, why do the ideas work? Could you apply them in different scenarios? Why or why not? What are other ways of thinking about the same problem? And then for problems where you really have no idea how to start, could you experiment and see what your experiments show you and try and decide what that means for the problem you're solving? So a couple of practical issues. I give opportunities to practice this kind of thinking in almost every single problem set. But usually they're the problems at the end. So if it takes you the entire block to do the foundational problems and then you never look at the problem set again, you might never have had the opportunity to practice that kind of thinking. So, it takes as long as it takes for you. You can't like speed up your speed on the foundational problems. But if you don't get to the end of the problem set, make sure that you look at it yourself at home later. Another issue is make sure that you're the one who gets to practice the thinking. If you're in a team with someone else who has a lot of practice at this way of thinking, they might read the problem and immediately say, oh, what if we look at the problem this way? And you didn't even get a chance to practice the thinking that was critical to that problem. They've already suggested the way of thinking, and now you're just applying the B-level skills to follow through on the idea. So a good thing you could do is you could try and tell your teammates, stop, let's work separately for 5 minutes. I want a chance to think about this. Or if it's too late and they've blabbed the answer already, or they've blabbed an approach already, you could ask them, what do you notice about the problem that gave you the idea? Or why did you think about it that way? I've never heard students asking that. I always hear students asking things like why does that work? But that's a slightly different question. It's also a good question to wonder about. But what you really want to be able to do is look at this unknown problem and have the idea that your partner had. So you need a question that will let them sort of tell you what it was that told them that they needed to think about it in a new way, and why it was that they thought about it in the way that they did. Why did they think graphically instead of algebraically? Why did they think about, whatever it was? So again, I think students, you want to be efficient, and I get that. But being efficient and focusing on how do you get the answer is not developing the kind of thinking you need. So you want to try and make this change in your thinking all the time. Change from what are the steps, what's the procedure, to all of these other things. This might change your approach to what you write down during your notes. It might mean that you take notes during and after problem sets. I keep encouraging students not just to take notes during the official notes time, but to take notes later, because the problems aren't there just to test if you got it. In courses where you can, where you're just learning procedures, the purpose of problems is, can you do the procedure? In my class, the purpose of problems is not asking, can you do the procedure? The problems are designed to show you something new. So you very well might want to ask yourself for the problem, what was I supposed to see in this problem? It wasn't just testing to see if I could do it. It was showing me something. And then write those things down in the problem set. So things that you might write down in your personal notes were key aha moments or new things that you saw in the problems. Or it could be different ways an idea might appear. So for vectors, geometrically versus algebraically. you could try and carefully express the logic of an argument. So like the horizontal asymptote thing that we were doing. Can you write down the logic of the argument, which is different than like the procedural steps. A lot of students seem to ignore the logic of the argument entirely because they were thinking, oh, all you do is you look at those coefficients and that tells you the answer. But they weren't thinking, why does it tell you the answer? And then they got stuck later on when I asked other kinds of questions. So that's stuff you can do in class. Things you can do at home are, of course, work on Challenger A-level practice. You can also come up with your own problems to practice this kind of thinking. So one thing you might do is take a foundational problem that you know a procedure for and try and come up with a problem that looks as different as you can make it, but which you think can still be solved using the same approach. And then try and come up with a problem that looks as similar to the original as possible, but which can't be solved with the same approach. Just coming up with these problems is a great way to focus your mind on the difference between the surface appearance of the problem and the important logical structure of what makes it solvable using a particular technique. Aside from, focusing your mind on the right thing to come up with the problems, trying to solve them is also probably pretty helpful. For a lot of problems you make, you might be unsure. You might say, well, it looks really different, and I think I can solve it with the same approach, but I'm not sure. So that would now be a great opportunity to practice deciding if an idea applies in a new situation. If you can't, bring your questions to me. I love new questions, and I can maybe help you think about them or give you hints, but that's also a great practice you could do on your own. Oh, and that's apparently the end of my slides. So I've also made a handout that encapsulates some of these practical ideas. So change what you think about, take notes in a new way, change what kinds of questions you might ask in class, and then at home, ways to build your conceptual understanding, and then exercises to find the boundaries of your current thinking or the boundaries of particular techniques. So you can read over those. But an important thing I'm trying to emphasize here is breaking through to the A level is not a thing necessarily where you just learn more advanced techniques. It's an entire change in how you learn math and how you think about math. And it's something that you practice all the time. It's not a thing that you practice right before a test. Developing this ability to think is pretty difficult. And you can do it. I've seen students do it plenty of times, but it usually takes quite a lot of effort, and it doesn't happen right away. It comes kind of very slowly over a month or 2 months or 6 months. So if you're interested in trying to do it, I think it will pay off for the rest of your life. It will make you smarter, not just in math, but in a lot of different areas. But have no illusions. It will definitely take work. I hope this was helpful. I hope this is the beginning of our conversation and not the end. I would love, as you start trying to do these things, for you to report back and say this is really working or this really isn't working and here's why. And we can try and adjust it to your own particular case. Thanks very much for taking the time to listen.